Okay, so hello everyone, welcome to our this week Rigorous Efficient AI seminar talk. And today, we're glad to have the Jun, Yuan, Shangguan to give this talk, Low Latency Efficient Speech Recognition for the Edge. And Jun is currently a staff software engineer, research scientist in the AI speech team in Meta's Reality Lab. And she previously worked on R&D side for low latency streaming speech recognition products such as Amazon, Google. Jun's area of expertise focuses on the advancing state-of-art compression for AI models on edge devices, which covers model architecture and runtime optimizations. And she obtained his master's degree from the University of Michigan and a bachelor degree from the Dartmouth College. And now let's welcome Jun to give us this talk.
Thank you, Professor Yuan, and thank you everyone for inviting me here. Many years ago, I sit exactly where you're sitting to look at the industry as well as academia research. So today, the topic is going to be low latency efficient speech recognition for the edge devices. And before we even start, I want to talk about that I only got this understand this about myself, but in general, you want to figure out if you are a curiosity-driven researcher or if you're a problem-driven researcher. A lot of us are curiosity-driven, which means that you're asking the question, what if? And you're possibly solving very long-term problem that may not have a need at this moment. An example is deep learning in the 1980s, 1990s. But if you're a problem-driven researcher like I am, you are actually trying to characterize the problem that you are faced and then characterize the constraints that you face and then figure out how you're going to solve each of the constraints. And so today we're going to approach low latency speech as a problem-driven research problem. So in today's talk, we're going to first look at the limitations that we face when we run the ASR on edge devices. We'll look at the common approaches that people take and also look at each of the constraint areas and the technique that we have developed to reach these constraints. And last but not least, we actually will look up on how we can scale up producing edge models for all the different devices that we have. Without further ado, let's look at the constraints. You are very familiar with it in efficient AI, but again, the model has to be very, very small. We're talking about 5 MB, 10 MB, or even less than 1 MB. The model has to be very accurate, even for an open domain dictation. So if tomorrow I want to dictate Harry Potter's spells, it better be correct on my watch, right? Or if I want to stream the model, for instance, I want to dictate the model while I can see the output as I am speaking. That's also very important for many of the assistants nowadays. So these are the hardcore constraints that we face when we run this edge device ASR. One of the common approach in the past is that when we face a speech problem, let's break it down into different sections. The first section is feature extraction. Typically, you do fast Fourier transform, do a log-mel filter over the transform, you extract log-mel features. And then you model the acoustic sound of each frame. Each frame would be typically 10 to 25 milliseconds. For each frame, you want to have a phoneme attached to it or classified as a phoneme output. A phoneme can be the phoneme is the basic units of the sound. So an example, let's say you want to model each frame of the wave, the spectrogram into C, silence, A, or T. The second part of it is pronunciation model, where you basically have a map between the sound to the actual word inside the language. And so this is typically graphing to phoneme, called graphing to phoneme model or graphing to grapheme model, where you just have a dictionary. You can train this model using a neural network. And the language model at the next step is actually just to predict the next token based on the previous tokens the model has emitted. So here, CAT-SIDS, you predict a MET. And last but not least, you need to combine all the probability distributions or probability of all the likelihood into one finite state transducer. And that's where the decoder sets in. The way the finite state transducer of the decoder will basically absorb the probability on its input edges and the output probability, emit output probability as well as the token as you go around. Today, we're going to look at mostly the modeling side of it, but not the decoder side of it. The decoder itself deserves a whole lecture on it. And so this is typically called the hybrid model approach, where you have acoustic model and language model separated. But recently, in the recent decade, there was a lot of growth in terms of end-to-end modeling. So the intuition here is that you're training each model with different loss function, and you're evaluating the model using word array, which is through the decoder, you look at insertion, deletion, and substitution with respect to your true ground truth transcript. So the acoustic model is usually trained with a cross entropy loss, or a loss called CTC, which I will elaborate soon. Pronunciation model can be trained using neural network using C loss. Language model, usually we look at perplexity. In a very simple word, perplexity is if you look at the expansion of the next token, how sure your language model is with respect to the probability of the next token. So the more unsure it is, the larger the perplexity, which means that your language model is low quality. So these are the loss functions you use to train each of the model. So if you are an eagle-eyed audience, you will find out that this whole network is not trained using what you're evaluating the network for. And that could create some suboptimal issues. And that's why the end-to-end model comes in. For the end-to-end model, you're looking at combining all these acoustic pronunciation language into one model. And then you use the decoder to find out the end best hypothesis. And normally when we train end-to-end model, we use its own model architecture loss. So here we're looking at a very specific paradigm of end-to-end. Just to explain, end-to-end model has many variants. One is sequence-to-sequence model called listen, attend, and spell. One is if you're looking at a streaming model, there's another one called Rnnt, recurrent neural network transducer. And these models are trained with different losses. And today we're going to mostly look at recurrent neural transducer that is from this citation number 5. Okay. So why do we favor end-to-end model for many of the applications? It's because now when you have one singular model that could model acoustic pronunciation language, you could be very small. And then you can actually teach this model using the loss function you actually evaluate the model on. And last but not least, end-to-end model could be made streaming and have low latency. So that really satisfies all the constraints we want for on-device. So let's look at this particular model architecture for Rnnt. In this model, we have a predictor network, which is actually analogous to the language model. So you take the past predicted tokens and you turn out this embedding of the likelihood of the next token. So it's an embedding of the past tokens. And the encoder part of the Rnnt actually is analogous to the acoustic model. It ingests the features each frame of the audio, and then it produces an embedding layer of the features. And the joiner network basically concatenate or adds these embedding together. And when we go through a softmax, we predict the next, basically the likelihood of the next symbol. The symbol here can be alphabets. If you're looking at graphings, it can also be sentence pieces, which means that in NLP, you can have word pieces, parts of the words, and that's what we are looking at today. We'll have sentence pieces target plus a blank symbol to indicate silence or no emission. So the Rnnt itself is really a beautiful combination of language and acoustic model. So now let's look at the Rnnt loss. the whole concept is actually quite simple. Basically, when you look at per frame label of your targets, let's say phoneme in the past, you can have hello as HEE, epsilon is blank, and then L blank, whatever. So here, we can find out that we can collapse the repeated tokens together, and then we can ignore the blank. And now we can map it to our ground truth transcript, hello. And you can easily imagine many different ways to write this hello in a per frame fashion. So basically, a lot of the different predictions of the acoustic model can be mapped to the same ground truth transcription. So this is called the connectionist temporal classification method, or connection temporal classification loss. And if we apply a similar idea to the Rnnt model, then let's look at the right-hand side. The vertical axis is the sequence of tokens. The horizontal axis is the time frames. So each time 1, 2, 3, 4 correspond to an input frame. And the model itself is basically traversing through this lattice to produce the final transcript. So if we take this 3-2 position as an example, if this token from the left is traversing horizontally, means that it didn't emit any token, it emitted blank epsilon. And if this 3-2 position is traversing vertically to the next one, it emitted one singular token. So you can actually map out for each of the nodes here. For instance, 3-2, all the alignments from this 1-2, all the alignments from 3-0 going to it are the same. Basically, by doing so, now you can easily define your loss function for each transcript alignment. So in the Rnnt loss, we define forward and backward probabilities. The forward probability is basically the sum of all the alignments from 0 all the way to this current node. So let's take 3-2 again as an example. So you will sum up the left probability of the left node plus this 0 emission probability and the probability of the node below plus the token emission probability. And that's what this first equation is talking about. The Z is the transition matrix of emitting a blank given t-1 and u position. And similarly, you can actually define backward probability beta using a similar method, which means that this 3-2 can sum up backward probability from the node above and the backward probability from the node to the right. So that's what the second equation is. The probability of any alignment in here is the forward probability times backward probability for all the nodes that will be aligned to this ground truth transcript. And so you can basically represent the loss function as the negative log of the probability. And because of that, you can actually do a differentiation and get that this gradient basically is forward probability times backward probability only if the backward probability is on its alignment path. I will highly recommend, if you're interested, to look at this loss function, to look at number 6, this citation here. But there's a reason why I'm introducing this loss function is because later when we touch on latency, you will see that the model kind of learns to cheat. It learns to emit these tokens at the very last step of the time so that it has more context and get more accuracy. But as we go along, it will be more apparent to you. Okay, so without further ado, now we have introduced the basic concepts of Rnnt and end-to-end speech recognition model. Let's look at some of the innovations that we have developed. First, let's look at the trade-offs or the requirements. As you're very well versed, we need to have very low memory and very low power consumption. And this is absolutely needed because when your model is running with higher memory than the system allows, the OS will kill your model. And that is very undesirable for consumers or users on the other side. Your model has to be running with very low latency. And that also sometimes means that you have to run the model much more frequently than a non-streaming model. You probably have to run the model every 100 milliseconds or so. Last but not least, we really want this model, on-device model, to be as good as server-side quality. And there's a reason, is because users or consumers, they expect very good outcome from on-device model, almost as good as what they're used to on server. And more importantly, the downstream models, such as the natural language processing model, will expect similar quality transcripts. And so if your model cuts off audio earlier, or if you turn out numbers differently, the downstream model will report error. So these are very, very challenging questions that we or constraints we need to meet. Let's look at each one. High accuracy is actually the easiest one, in which we basically look into the best model technique in industry. And so, like we started off on linear layers, super simple model. You can build a lot of MLP model, but because you're running on device, you want to be very compact. And so each layer should represent high-level nonlinear information at its most capability. So we first tried LSTM-based layers. If you're familiar with the equation, the input gate, forget gate, input block, and then a LSTM hidden layer. So we also transitioned into augmented memory transformer. So being very inspired by the transformer wave, we basically look at how we can model speech using transformer layers. Here's a very interesting work done by my coworker, Yang Shi. The difference between this and a typical transformer is that it's streaming, which means that you only have a limited context on the left-hand side. You don't wait until you see the entire sequence. The way you achieve that is that you chunk the audio input into a chunk C, and then you fix the left context L. You have some access to right context, let's say 1 frame in the future. And then you also append something called the memory blocks, and the memory blocks is carried over from the previous layer and previous segment. So here's the typical key, value, and query matrices and the attention mechanism. So the attention only reaches the left context, and the memory block kind of a history. It doesn't look at the entire sentences. And you can see this is very similar to transformer, but much more efficient in its computation. Last but not least, I noticed that in industry, there's a lot more interesting cell architectures. One of the cell architecture is a context net, and it's all convolution based. So let's say you're in a research lab, you feel like transformer needs a long time to run, and CNN use less time. This might be a good architecture. So it's basically stack blocked of convolution layer, batch norm, and activation layer. At the end of it, you have a squeeze and excitation layer, and then you have a highway on the top through convolution and batch norm. This layer actually produced one of the state-of-the-art results on LibreSpeech public data set. On the right-hand side is a conformer layer. It's a combination of multi-headed self-attention with convolution. And this also yields really good results on state-of-the-art results on LibreSpeech. So as you can see, for on-device speech ASR, we have been consistently following the latest trend in like vision or NLP to pick up latest model. But we have our own challenges, and the challenges in low latency. And this part is actually quite interesting because we first need to define what latency is. And only when we define the problem crystal clear can we solve it. So in this paper, me and my co-authors look into how exactly do you quantify latency, and what exactly are the factors that impact latency. So this is a very complicated graph, but I want to just show you that this middle chunk is the timeline of the user comment and some silence at the end. So when the first chunk of audio reaches the model, we start counting. When the last chunk of audio reaches the mic, and then we start another timer. So now your model, as the first chunk starts to reach your model, you start to process the frame by frame, right? Like chunk by chunk, but it's possibly processing the chunks a little slower than the in-stream audio. So by the time the last audio reaches you, you're not done with the previous chunks yet. So you're processing a little longer until you're totally done. The Rntt totally says, I'm the end of sentence. And then this is where a end pointer sets in. And the end pointer in ASR typically defines when to close the microphone. So it starts counting silence from at the end of the emission of your Rntt model and starts to wait until enough silence has been achieved and it ends the microphone. And so the speech perceived latency is actually the sum of your decoder catch up to the end pointer closes the microphone. So we define it as the point when the client stops speaking to the point where the microphone is closed. And this is a very reasonable definition because the downstream, let's say NLP tasks, waits for the microphone to be closed before they start running. And so this latency is definitely being passed down if you have an application like Assistant. So if we define the latency so crystal clear, it is apparent to us that what are the things that might impact latency, how fast your model is running, and how fast your endpointer, how accurate your endpointer can endpoint. So the first thing we want to do is to say, does any of the traditional metrics that people report on their paper impact latency? Do they reflect exactly what the latency is? And the answer is negative. So let's look at some of the traditional things that we report on academia papers. RTF, real time factor, is defined by the ratio between the amount of time you need to process 1 second of audio. Flops, easy, just counts the number of computations. Model sizes, just number of parameters in the model. Model stride in ASR means that how many frames you wait until you run one forward function. So these are the common things that people report as say, look, my latency is low because my RTF is low. So we did a comprehensive analysis of that. I want to draw your attention to this table. It's pretty dense, but the ABC on the top is LSTM based. We use LSTM cell to build out this Rntt. And model D is we use the informer, the efficient transformer to build the Rntt. And if you look at the sizes, they're converted into MB, but it's equivalent to the million of parameters if you look at it this way. This is 50 percentile user perceived latency, our target. And here are the other matrices reported. So if we look at model B and model D, these two models have similar UPL, user perceived latency, but their RTF is drastically different. So is their size. And so neither is flops, RTF, and size here indicative of what the latency actually turned out to be. And similarly, you cannot look at model sizes and say, oh, their latency would be reflective in the model sizes, even with the same modeling cell. So as a result, we feel that none of these pseudo metrics really reflects what on-device latency is. And so we went further to look at what exactly are the factors, and we actually grouped them into 3 categories. One category is model design. How fast is your model depends on how you design the model, what's the loss function you use. The second category is endpointing design. What kind of endpointer are you using? And the third category is other factors like runtime, like quantization, sparsity. These techniques shrink the model and make it faster. But in this paper, in particular, we focus on the modeling side of it. We'll mention the other factor in the subsequent segment of this talk, but let's look at the model design first. The key insight, as I explained earlier when we explained the Rntt loss, is that the Rntt loss allow you to emit a lot of blank and then wait until the last moment to emit the token. So that actually, we suspect that the hypothesis is that allowed the model to have longer latency, but better quality. Remember that latency is always at odds with quality. So we want to measure these in terms of quality, wear rate versus latency in the same graph for our paper. So let's look at one example of what we mean by token latency delay. In this matrix, in which the vertical axis is the tokens, the horizontal is the time, we first do a hybrid model alignment. We basically take the ground truth and say, okay, which frame is the most probable that the token was emitted? And the alignment shows us the ground truth is the blue one. But the Rntt actually ended up having a token end time of the black one, which means that the token was emitted only after this many times. And this is an example to show you what we're seeing every day, is that the token gets emitted much later. And so my coworker and I thought about it and say, we need to restrict the alignment so that we can emit the token early enough to meet our latency requirement. And so this is alignment restricted Rntt. So instead of summing all the path in the lattice up to this point of the token, we actually only care about the summation of the path around your ground truth emission, which means that in your lattice loss computation, we modify this transitional matrix. Remember that the transitional matrix basically is the probability of the token from the left blank, a token from the bottom for emission. And here we only set it as non-zero if we see that the token is emitted from within this bracket. This bracket is defined by a left boundary and a right boundary. You can emit at the extreme end of left boundary, that means early emission, or the right boundary, which is a controlled late emission. By doing so, now we force the model to emit token within this ground truth alignment. And let's look at the result. I want to draw your attention to the graph on the right-hand side first. The blue line is AR Rntt. We now present to you the word error rate, which is the error rate of the model, so the higher the worse, and the token average emission delay. So we just take the average of each token's delay and plot it out. And so we started off from just a basic standard streaming Rntt as the red cross over here. And the blue line is AR Rntt, but varied by the difference of the right context. So remember that right context is how much more delay I allow it to have. And so we started from just all the right context, all the way to very little right context, as you can see from the third column here, BR. And we noticed that AR Rntt allow you to have a fine-grained control of the Pareto from a wear rate versus token emission. And this is not doable with any other technique, such as mono LSTM, or we also compare this to non-streaming LSTM, in which you can see that if you have a non-streaming model, it actually emits the token a little earlier, but that's not doable because we need a streaming model. Also, a side effect of latency control, let's go back to here, is that because you're no longer summing up all the lattices, you only look at this band of path around the ground truth, you can compute your model 4 times faster on GPU, which means 4 times of GPU resources saving if you train with alignment restricted Rntt. So on the left-hand side table, we're plotting now alignment restriction with respect to the right-hand side allowed token delay. And the quality is in terms of the Libre speech, test clean, test other, as well as the token delayed average delay. So you can see that if you just do 0, the model was able to emit immediately on the ground truth time, but yes, there's a degradation for wear rate. And so back to the problem of latency. Now we have developed AR-Rnnt. Let's look at how it affects our user perceived latency. So in this case, let's look at A and J1. Our token delay has drastically improved with AR-Rnnt, and so is our 50 percentile and 90 percentile UPL, user perceived latency here. And we also break it down into decoder catch-up versus endpointer. We found out that even if the decoder catch-up hasn't changed, which means that the model per step is still kind of the same amount of time, because your last token was able to be emitted early, your endpointer started counting silence early. And that's why the endpointer has a huge reduction in its latency. And of course, you still see that the wear rate has some degradation because of that. Okay, is there any question with regard to the alignment restricted Rnnt loss? Okay, if there's no more question, let's look at the next factor that impacts on-device latency, and it's the endpointing. We want to explain the three kinds of endpointers we use. The static endpointer basically starts counting as the model emits a epsilon, a blank, and it counts until a certain amount of silence and closes the microphone. So it's a very mechanical way to determine endpointing. Neural endpointer is a very lightweight 1 megabyte model or 2 that actually models silence versus non-silence. So it also has a threshold. So if you have a probability beyond this threshold for a certain amount of time, we close the mic. And the end-to-end endpointer is much more interesting, where you actually add a end of sentence token to your Rnnt. So you use the ASR model to predict endpointing. And so during training, you know exactly the utterance endpoint, so you can actually backpropagate that probability. And so the E2E endpointer is basically ASR predicted end of sentence token. And so if we look at these three endpointers and how they impact latency, again, we plotted out the quality versus latency on the two axes. Let's look at the blue graph first. The blue one, the blue curve here, is different threshold of the static endpointer. And so as you set a very sensitive, very short amount of silence, you definitely have a much better user perceived latency, but the quality is unbearable. And the reason why the quality is so bad is because you're cutting off a lot of people when they're just hesitating. Let's say, hey, wake word, do something. And if I hesitated for a split second, this endpointer would stop. And so our goal is to push this Pareto fund to much closer to the 0 point, right? So that's where we want. And hence we added neural endpointer and end-to-end endpointer to here. And the graph here, we blow it up to the right. And so we first add a neural endpointer. Immediately you see an improvement of the quality at a given latency. And when you add end-to-end endpointer, and the curve improve even more. And this is interesting because it tells us that static endpointer, neural endpointer, and end-to-end endpointer, they are all complementary of each other. All they want to achieve, combining them, what we want to achieve is the most accurate result to predict when the sentence ends. And so now in this final result, we put everything together. I will walk you through it. There's a lot of dense things here. We have user perceived latency in this in the third column. We have the model striding in the second column, and the decoder catch up and endpointer. So here, the striding is basically I wait for 2 frames or 4 frames before I run a forward. And so, as you know, the more frequently you run, likely your user perceived latency should be lower. But in this case, because you run the model frequently, your real-time factor is high, which means that your decoder catch-up is high. So there is a really fine balance of how many frames your model wants to process. We plot this out in this graph on the right, in the red. So you can see that there is a sweet spot. So when we run at 8 chunks, at a stride of 8, the model performs the best. And so from there, we added AR-Rntt alignment loss. Immediately, we jumped to J1. And then when we added better endpointer, neural endpointer, as well as the E2E endpointer, we were able to achieve J2 and K. So this is the progress in which we have made to make the model still very reasonable in wear rate, but much lower in latency. So that sums up this dissecting latency paper that we have tackled latency. Before I move on, I want to ask if anyone has any questions on this. If not, I would like to go to the next section. Cool. Let's go to the next section on low memory and low power consumption model. So we mainly achieve this through model compression. And this is also a work done by me and my coworkers for HML. And the first technique that we use to compress the model and make it much more friendly to run on hardware is to swap the cells. Like we use the LSTM cells. There's a lot of matrices and recurrent layers in there. And one of the very tested and proven technique is to couple the input gate and the forget gate. So in this case, you have one fewer gate to compute. So you save around a quarter of your computation. There's also a new cell architecture coming up called the simple recurrent unit from MIT. In this case, you only have two gates, forget gate and reset gate. And the internals are computed using these gating mechanism. So we take these ideas and we take these cells and we swap the encoder of the Rntt as well as the decoder of the predictor of the Rntt. So in this case, the first line of the second column is the encoder. And the second part is the predictor, the LM part. You can see that the encoder actually occupies a majority of the weights of the model. So as we swap things around, we see that, okay, the quality of replacing the predictor with a much smaller cell, SRU, is actually quite good. If you look at row number 3 versus row number 1, and we can see that there is obviously an improvement of the model size with respect to the baseline. And these are computed as million parameters. But if you actually swap everything with SRU, then the model quality degrades drastically. This observation actually is very interesting because right after this paper, there's a couple of coworkers found that the predictor of the Rntt actually is quite useless, and they swapped out all of these cells with an embedding layer. So this is there's another paper called the stateless Rntt that exactly describes this. So for us, we saw the same thing. Like the SRU is enough for the predictor. And so after we swap the cells, we turn to sparsity. And that's a very natural thing you want to do if you want to compress the model. And here we use block sparsity because it's more friendly towards CPU architecture or the kernels we designed. And the block is pretty big, 16 times 1, which means that consecutive 16s are actually all zeroed out or non-zeroed out. So in terms of sparsity, we have discovered a couple of very important things that will make the sparse model good. The first thing is that we should be able to rediscover previously zeroed out items if we found that some new blocks are a little less important than the previously zeroed out items. So we will rediscover them and zero out the new block. And so by doing so, we are always updating the mask, even if we achieve the target sparsity. And we found that that's quite important for this model. The other thing that we found is that we follow this pruning schedule by this Michael and Suyog Gupta's work to prune or not to prune. Despite the amount of literature out there about lottery tickets, we always found that for our models, just having a gradual pruning schedule from scratch performs the best. Sometimes we see the model with a well-trained model and gradually prune it. So we present the sparsity imposed on LSTM Rntt here, where you can see that as you increase the sparsity, naturally the wear rate degrades a little bit, but it's quite impressive that even at 70% sparsity, the degradation is very small. Now we can combine the two techniques together, alternative cells with sparsity. And so here we found that if we use CIFG couple input gain for get gate LSTM in the encoder with a 50% of sparsity and the SRU in the predictor with 30%, we get very good results. It's very interesting that, and also the model is smaller. It's very interesting that we also tune a very strong baseline. We basically downsized the LSTM model to 0.7 of its size, and we didn't use sparsity here. We see that surprisingly, the wear rate is like a lot worse. We were not expecting this. But one thing that is worth mentioning is that because of the sparse indexes and matrices, you do have to have slightly more RTF because you're unpacking the layers and you're computing the with sparsity. So it's not exactly a faster computation, but it definitely is a smaller model. Last but not least, I am sure all of you are very familiar with is quantization. Basically, we tried both integer or static quantization versus a dynamic or what we call hybrid quantization. So simple concept, the quantization is to take the weights and redistribute it into a fixed amount of bins. One of the things that is worth highlighting for this speech-specific model is that we have a lot of layer normalization. We do not use batch norm in our models. Layer norm is actually very difficult to be statically quantized, which means that the activation has to be quantized. That's because in the typical layer norm computation, which is the first and the second equation, we observe that 99% of the weights of this activation is within -3 to 3. So when you want to quantize that, the definition is not very good for quantization. So the way we went around it is to basically give it a constant to scale up the activation scale, and then at the end of the quantization, we scaled it back. And this has been actually tremendous to help with the accuracy of the model after static quantization. We do not do training aware quantization. It is totally good to do it, but in this case, we just want to take an off-the-shelf model and be able to statically quantize it. And so the results are presented in this kind of grand visualization. On the vertical axis, again, is the word error rate. And on the horizontal axis, we use model size. You can go ahead and look at the paper version 2. You will see RTF as well. So we started off from a dense LSTM Rntt. And as we add 50% of sparsity, we were able to shrink it almost by half. And then as we add quantization and swap the cell, we were able to achieve to this yellow dot where the size is about half of, it's about 55 megabyte, and the quality is also very good. So you can see, roughly see the Pareto front right here for this model. Cool. So this is very exciting, but all of this technique work for on-device ASR, but so far, all of our edge models, ASR models require deep learning expert. It requires PhDs like you guys tuning the model, knowing exactly what's happening and working on it. But, you know, we support a lot of models and we want to make sure that what if we just train one model and it can optimally produce all kinds of smaller models that is optimal for their sizes. This is a very challenging, imaginative question. And so for our case here, we are looking at this problem through sparsity, because sparsity naturally has this setup where the underlying weights of different sparse models can actually be shared. And so in our case, we look at individually training K model. You will maintain that K model and you will have K times more training time than one single model. There is a work called dynamic sparse neural network, which I will elaborate on later. It's done by Google, and it says, okay, let's share the weights of the K models. All of them share the same underlying weight, different mask. However, during training, they actually train each model separately. So you still have K times 1 training time. In this work that Haichuan, Diling, and I do, it's basically we train one model and we use exactly one model's training time to produce all kinds of sizes. And let's look at how it's done. The dynamic sparse neural network, as cited here, uses a loop. Basically, for the sparsity that you have defined and that you want to train, and you get the pruning mask for that sparsity, and you run a model forward. And so you're running this loop inside a batch. For our omnisparsity model, this has changed. We split the batch into smaller mini batches. For each mini batch, you randomly sample a sparsity from the search space, and you train forward function. And the same number of the model sample is the same number of mini batch we split. So that means you are always training with the same amount of data and same amount of training GPU time. So let's look at the schematic of it. For each layer, we define a search space. For each layer, you have 5, 6, 7, or 80% sparsity. But during training, you can combine different sparsity per layer to sample different sizes of network. So that's how we do during training. At the end of the training, when I said, hey, I need a 75% sparse model, the way you do it is to run an evolutionary search where you generate configurations for each layer with different sparsity, and you look at the ultimate sparsity of the entire model. It should be around 75%. So here's an example. We merged the 80% bottom with 60% bottom with the 80% top, and now you create 2 layers with 75%. So this is how we were able to churn out any sparsity you desire within the range that we have. My Google Assistant just woke up. So there are actually some really big difficulties we face when training this kind of network. The first difficulty is that it is hard to find the pruning mask based on this kind of scheme. Traditionally, we find that people use L1 norm of the pruning mask of the weight magnitude to find the pruning mask. We found that gradient times the weight magnitude is a lot better indication, because the gradient tells you how important the weight is. But in this case, when we're training, the gradient is a little bit unstable because you're sampling only a subnetwork each step. So that imposes difficulty during training for omnisparsity. The second problem is that we do not have the luxury to sample all kinds of possible models from this one single supernet. And the third difficulty is that regularization of the model should be adjusted to the model size. We all know that the smaller your model, maybe the less regularization should be. And so we actually came out with 3 different mechanisms to solve these problems. I will wrap up very soon, but the mechanism we have is for each batch, we do an in-batch sampling, but we only sample 4 models, the biggest, the smallest, and 2 random models. And each model sees a quarter of the batch. We also use adaptive dropout, in which we scale the dropout according to your sparsity per layer. So we scale that particular layer's dropout according to the sparsity at that time. Last but not least, we actually found that we can use the second gradient moment of the atom optimizer to choose what ways to prune and what not to prune. And this has been huge. This fundamentally changes the quality of the model. So without further ado, let me show you the result. It's very impressive that if you manually tune this strong baseline, you train the best model you can at these sizes. And versus we train one model, we just do evolutionary search to find the best model based on validation loss. So the way you do it is per layer, you generate some configs, and basically you can randomly permutate the configs, randomly mutate it or crossbreed between configs, and you can select the strongest config based on validation loss. So this is a very traditional evolutionary search mechanism. So we were able to find all these models at different sparsity and different word array. And you can see that the Pareto front is being pushed to the optimal Pareto front. And one of the questions we ask ourselves is that, is it because our model is better, our omnisparsity is better than singly trained model because of in-place KLD? Is it because we have in-place KL divergence that is implicitly building into the shared weights? To validate that, we actually take the singly trained model and apply KL divergence of that model with a 0% sparsity dense model. So that's the last column of this one, where we take the originally singly trained model from the first column and KLD it with the dense model. We see better result in test clean of Libre speech data set, but we do not see better result of test other compared to our omnisparsity model. Not even mention that this model actually requires 4 times more GPU hours to train than omnisparsity model. So when you look at GPU hour, our technique really surfaces as the winner, because we train 4 models and the dot size correspond to the model size. With only 4 models, we can train a very, very good quality with a very small GPU hour. And for the dynamic sparse neural network, because you're training each model individually, basically, you don't save any GPU hour. Same with the singly trained model. But what's more exciting is that our model, the training GPU hour does not scale with respect to the number of model you generated. However, the other 2 methods will increase their training time if you need more model at different sizes. Last but not least, we also did ablation study of the things that we mentioned, the atom pruning and adaptive dropout. So let's first look at this ablation study, table 3. On 2 different sparsities, we basically turn atom pruning on and off, or adaptive dropout on and off. We see that they do actually incrementally improve the model. Last but not least, we also want to ask ourselves, is our model from the omnisparsity supernet the best at its Pareto front? So the way we look at it, we try to quantify it, is we take that model, we add some individual model fine-tuning. So we take the generated model, we fine-tune the model to see if it can get improvement. If it can get improved, that means we're not at a Pareto front yet. And in this case, no matter how we fine-tune it, either individually fine-tune it or fine-tune the supernet even more, we don't see much of improvement. That means that the model generated from omnisparsity supernet is indeed at the Pareto front. Okay. Oops. So that concludes our recent work on omnisparsity network, where we were able to train one network and generate many smaller networks. And this concludes my whole talk on on-device, edge device ASR. And I just want to mention that some of the takeaways that we have talked about today. We went over the end-to-end Rnnt framework. We went over how loss function can be improved to control latency perfectly. We also talk about sparsity quantization that we can do to shrink the model. Last but not least, we show you how you can train many, many models from one training job using the same amount GPU hour as one job. And I really like to thank all my mentors, co-workers, and co-authors. Yeah, sorry, this talk went a little long. Yes.
Thank you. Thank you, June. Thank you very much for the talk. And any questions from the audience? So you can unmute yourself or input your question in the chat box. Yeah, I think there's one question in the chat box. Can you see that?
Oh, I see. Sorry, this is my first time using chat box. I cannot see the chat box. Could you tell me what the question is?
So can you mention 1 to 2 top killer applications of on-device ASR? Would you also comment on ASR versus SLU on device? Okay.
So there's, let me put it this way. A lot of the products that you're familiar with, let's say on-device transcription on Google phones, or on-device caption, where you have the privacy without connecting your speech to the cloud, but you can still get high quality caption from the videos you're watching. So you do not need to actually turn off your volume to know what the video is about. So that's one application. The other applications are such as assistants. So common ones are Alexa, Google Assistants. These are also very popular uses. And when it comes to SLU versus ASR, we understand that ASR is the front or the previous pipeline of SLU. So spoken language understanding it could include ASR, but it also includes natural language understanding. Whereas ASR purely is the pipeline where wave comes in and transcription comes out. There's no intent prediction. There is no slot prediction. So that's the difference between them.
There's another question. So is the code available on the GitHub, particularly Rnnt?
The code is available on PyTorch Audio. So PyTorch Audio is open source. You can look into that. Also, the Informer cells are available there as well.
Another question, can you quickly clarify more on why the gradient pruning method is better?
Yes. A lot of people just use magnitude of the weights, and this works for image because the magnitude of the CNN is very correlated to how important it is. But that's not necessarily the case for speech applications or for NLP applications, because when you look at the magnitude of the weight, it could be a very big weight, but contributing to the forward or backward gradient very smallly. So for us, using the training gradient indicates how important is this weight contributing to the ultimate loss. So we use weight times gradient as a way to look at the pruning mass, and it's been very helpful. But as I said, I think the most effective one that we found so far is atom pruning, where you use the acceleration or the gradient of the gradient to look at the pruning mask. Yeah.
Is there any other questions from the audience?
Hi, Professor Chun. Regarding sparsity to improve the performance of a network, do you need a special kernel to realize the actual speed up or reduce in latency?
Yes. Yes, you need a special kernel. And you do also need special kernel to realize shrinking of the model. And these kernels, it's already open source in PyTorch kernel library, but just a quick explanation. These kernels need to represent the dense, the specified weight matrices as block and row stack indexes of the non-sparse blocks and the value of the non-sparse blocks. So by doing so, you can really speed up the computation. But I cannot say for all because NVIDIA has recently come out with a sparse kernel in which they were able to speed up sparsity by having 2 in 4. So 2 out of the 1 times 4 is sparse. You can also speed it up without the block row column index representation. But overall, the answer is yes, you do need special kernel to speed up.
Quick question, is the NVIDIA kernel open source or no?
The NVIDIA code for speeding up sparsity over GPU is available. And there's a caveat, you have to use NVIDIA 800 and above GPU in order to realize that. V100 doesn't have that. Yeah, you can see the blog post. It's all listed right there. Yeah.
Okay, thanks.
And there's another question. Would the ADAM pruning be effective in image models too, compared to the more common weight pruning?
So I do not know this answer because I haven't seen anyone trying ADAM pruning in image model. But I have seen a couple of work on gradient pruning elsewhere. So if you want, that's your paper.
Other questions? So actually, June, I have two questions. And the first one is that, so in your presentation, I think the backbone model is still the like Rntt, right?
Yes.
So I was wondering, so have you ever considered that to completely replace it with the purely transformer? And if it doesn't work, so why? Since right now in the NLP and computer vision, the transformer is kind of become so popular. And the second question is that, so about the trade-off between the accuracy, like the WER and the model, and the model size. So like in some of your slides, there's some like we can obtain 5 times compression ratio with the penalty of about 0.5-0.4% WER increase. So I was wondering, so from the perspective of the practical applications, so what extent of such trade-off is kind of acceptable from the perspective of the user experience and so on? Yeah, because we know that, like, for example, in the research domain, like in the computer vision, typically we want to have the no accuracy loss and so on. But how about like for the ASR?
Yes, these two are extremely good questions. So let me answer in different ways. So first, to address your first question, I think we should get the concept of Rntt as a model paradigm very clear from the cell structure. So the model paradigm is how you construct the model, how models run each component. But the model cell is what you use to construct each component. So we do use transformer-based informer cells to construct the encoder. So it's not a pure transformer model, as you mentioned. And yes, there is actually sequence-to-sequence model or even streaming sequence-to-sequence model out there. There's one model in particular called MoCA, monotonic chunk-wise attention model. So it's a sequence-to-sequence attention, but they constrain the context into a streaming context. So instead of attending to the entire sequence, you can attend to chunks of the audio. Unfortunately, I haven't seen I haven't seen that MoCA has transcended Rntt yet. I think these two are comparable. There's a lot of engineering involved. And the second part of it is why Rntt is so effective. It's just, we were able to tweak around, different parts of the model, run on different chips and different optimization. I do think that if we invest a lot of time into purely attention-based sequence-to-sequence model, we probably can get there as well. So the answer is indeterminate. I do not know exactly why we didn't use it. To your second question, to the wear rate trade-off. Yeah, that's a very good question because I cannot say this is not for any specific product, just my own personal experience, 10% of wear rate, totally tolerable for most products. And that means that, and sometimes imperceptible. And let me explain why. A lot of the word error rate is due to small words being replaced, excuse me, like the, THE replaced to a, like the cat versus a cat. It doesn't impact people's understanding of the sentence. And so because of that, actually our field come out with a new measurement called semantic distance. It's also by my coworker, where you measure the semantic embedding differences between the ground truth transcript and your transcript, rather than just word by word, what's the difference. And if you look at that, I think it's very reasonable. You can compress the model quite a lot without hurting semantic distance. Yeah, so very good question.
Thank you very much. And, other questions from our audience? Okay, so if no more questions, let's thank our speaker again. So thank you, June. So this is a very excellent talk, and actually we learned a lot from your talk. And also thank everyone to attend our today's seminar talk, and our next talk will be on next Monday. Okay, thank you, June. Thank you very much.
Thank you. Bye.
Thank you. Have a wonderful day. Bye.